Welcome back, and given these really exciting sessions, I think we are set up for a great panel discussion led by Dan Stamper-Kurn, who's he's the director of CIQC, our quantum center on campus, and which also, of course, puts us in Simon's quantum research. So I'll let you introduce the.
Oh boy. Okay, I'm going to actually ask the panelists mostly to introduce themselves because they've been mostly on the stage. So hopefully that'll be okay with you. But actually, I'd like to start off the panel because we have two members of the panel who were not among the speakers. So maybe what I'll do first is just direct a question to them, and then they can introduce themselves by way of response. So I'll start with you, Jonathan. You're the Chief Scientist and co-founder at Atom Computing. Great to have you here. So here's my question for you. So I'm an atomic physics experimentalist, and in my lab, my grad students, when they're not on strike, they do experiments. They actually trap single atoms and measure their properties. So if I or my students walked into your labs at Atom Computing, what would they find that's the same, or what would they find that's very different?
It's on. Okay, yeah. I mean, what's the same is a lot of the techniques. A lot of Thor Labs lab snacks boxes probably would be would be the same. So I think a lot of the individual components and the techniques would look similar. They'd be in a familiar environment, and I think what would look different though is that I would say in industry, and when you're kind of building up the systems that we build, more and more of your time kind of changes over time from being in the lab building, playing with Thor Labs components, and you eventually always end up doing a lot of software engineering to actually build the infrastructure that runs your experiment, calibrates your experiment, and integrates it with the larger software stack in the company. So I'd say the focus on having at least some base level of software engineering skills is probably a difference. Or maybe a greater focus on software engineering skills.
I see. So others who have made the crossover into experimental work in industry, is that a similar feeling?
Yeah, I agree with that. I think that there's actually a lot of going from academia to industry. One of the things that I've come to realize is that we are now in charge of building all of the infrastructure, which is something that comes for free almost when you're in academia. So software is a big component to it. But the other thing is, while we do a lot of kind of proof of concept builds for next generation tools, the design process that goes into building new machines is very different than at least what I saw when I was in academia. There's really much more of an engineering drive to make things more reliable, to make them easier to reproduce, to maintain, and so on. So there's a lot of work that goes into modularizing things and standardizing them that I think is absent in academia.
Mm-hmm. Okay, well, I'm going to switch to something very different. So it's good to have Chinmay here. Chinmay was a PhD here at Berkeley, right? And now you're at IBM.
That's right.
And one of the things that one of your foci during your graduate work was working on this no trivial low energy states theorem, right? Which was an important outstanding theorem that, okay, now I'm going to butcher it, that says that there's a class of Hamiltonians for which all the low energy eigenstates are guaranteed not to be simple, in the sense that they would have been producible by a finite gate set from some product state to begin with. Did I get it right?
That's right. Yeah.
All right, great. So that's kind of a physics statement. I understand that from a physics point of view, but there's also a sense in which this is like a big deal for quantum computing. So can you kind of explain that connection and how far in inference we should draw?
Yeah, so it's this notion that are there interesting quantum systems which we might want to understand, which classically don't have good descriptions. That's one way to sort of put it, in the sense that if you were to try to describe it, it takes a really big circuit. Now, what does that mean exactly in terms of physics? Well, you could think of it in many ways. You could think of it as, hey, if you were able to actually construct this state, and you're able to certify that you created this kind of interesting topological phase of matter, then you have a provable complexity argument to back up that it's novel, a fundamentally different topological phase of matter. Another thing is, more broadly, is I think there's this nice touch in academia where you try to understand impossibility results. So much bigger interest in that, whereas in industry, there's a lot more of like, what can you do despite noise, despite all these things? So that's where these two things get along.
Mhm. But does it tell us, so what does it tell us also about, so I think that one of the connections, of course, between physics Hamiltonian models and quantum computing is through this idea of adiabatic quantum computing, right? So if I have a model which in its ground state, heck, actually in a lot of its excited states also has the answer to some interesting numerics problem, then there's a possibility of by adiabatic evolution of getting into that state. So is this NTLS telling us that that's first of all legitimate, but secondly, is it easier than we thought it was? That sort of adiabatic approach to quantum computing?
I don't think it actually says much about adiabatic computing. It's unfortunately a little bit crude in that it just says the circuit model, it takes a lot of circuit depth. And the reality is to convert from the adiabatic model to the circuit model, that there's some blow-ups there. So it's not exactly clear what it says about the hardness in the adiabatic model. But that's by itself another interesting question you could ask is, can I write down Hamiltonians for which adiabatic evolution is not a good candidate for solving these things? It would take a long time for an adiabatic algorithm, provably. That would be like a adiabatic NLTS statement. You could ask that, and that's really worth thinking about also. So.
All right, well, thanks.
Just one question, can
right.
this all be applied to the D-Wave system?
I'm not sure.
Okay.
So maybe I'll switch questions. So now that you guys have kind of introduced, anyhow, so you've moved now into working at IBM, and like what's the work you're doing there?
Oh, I am. I'm a complexity theorist. Actually, I don't think they let me even into the rooms with the devices.
It's complicated enough. They don't need you in there.
It's probably for the best. I think the worst thing I would do is probably step on something and break $1 million piece of equipment.
Okay, good. Very wise. All right. So with that in mind, maybe we can sort of explore a little bit the quantum industry landscape. So there's now a pretty wide sector of the economy that seems to be interested in and committing resources to quantum computing by various investments. So what do you guys see as the main driver for this broadened interest? Thanks, Sergio.
Not an easy question. What's the main driver? Where I think, I guess the main driver is first, it starts with good theoretical results in quantum computing, right? Basically, I would say results in complexity theory, actually, right? That we understand a fair amount of things about complexity theory. There is this thesis, the Church-Turing thesis, that says that different computational models are equivalent. There is a strong version of that says that different computational models are equivalent as well in terms of efficiency. And then along comes quantum computation, and I guess the hypothesis is that there are certain computational tasks that can be solved exponentially faster with quantum computers than classical algorithms. So I think that's a very big paradigm shift in computation, right? So that really sounds interesting. Then, okay, so that you have these nice, interesting theoretical results. There is, of course, a source algorithm that, of course, grab a lot of people's attention, meaning quantum computers in principle could break what is the standard method today of public key cryptography. So that will be, very interesting for some agencies, I guess, not necessarily for industry. and then on the other side, you can say, well, these are all nice theoretical results, but maybe this is all a pipe dream. This is always going to be magical qubits, as John was saying. And it turns out that there has been, since these results, which is already almost 20 years ago, I guess, right? Or more actually, getting to 30, then there was like a phase of, well, this is very interesting, but it's very hard. But then I think in the last decade, maybe there has been a lot of progress on the error rates of experimental processors, the way John and others were describing it. So I think it remains super hard to build a quantum computer, but it's starting to look approachable. It's starting to look, hard, but believable. So I agree with John when he said, like, if we don't improve our qubits, then maybe in 5 years, we won't be saying the same things. But, as John said, like, we think we can improve our qubits, right? So then we have, I think, a strong theoretical foundation for why this is an interesting endeavor from the point of view of computation. And then we have enough experimental progress so that it starts to look believable. So I think that's why, at least big companies that work on computation, like, I work at Google. So Google is what Google does is computation, right? So enough to at least make, some modest investment. It's not like it's the biggest investment at Google, but, for the size of Google, is certainly, it's a modest but important investment, I think, on what is the future of computing, right? And then there are other industries as well that are not just computation, but I guess there is always a little bit of fear of being left behind, but that, so I think it's probably appropriate. If you're not building your own quantum computer or having your own quantum computing group, you want to have some knowledge of how the field is evolving so that it doesn't happen to you, like, I don't know, with electric cars, for instance, that then, electric cars is the thing of the future until it's not. And then there is some other company that is dominating that market, right? So it's still very early days. I don't think it's going to be, it is not a profitable investment right now in terms of commercial returns. It can be, profitable in other ways, but it's certainly not generating profit. It's not solving practical problems today, but depending on your industry, 10 years, which is what I think we're more or less estimating that if everything goes well, will take to build a quantum computer. 10 years might not be such a long time. If you're, Goldman Sachs has been around for 150 years, right? So they probably, if you say 10 years, it's like, well, that's not so much. I don't know. So maybe some companies want to make sure that they at least are not going to be surprised, and that doesn't require a huge amount of effort. And then other companies which are more computational, they really are starting to see the promise of quantum computing. So as long as it has a strong theoretical foundation and we keep making progress experimentally, then I think we're gonna, keep seeing those investments moving forward.
And you grabbed the mic because you wanted to chime in.
Yeah, let me try to give it just a little different type of answer, which is, look, I think the last couple of years have been years of serious turmoil worldwide in a lot of ways that have upended a bunch of assumptions and have reminded us that, there are some serious potentially existential crises that we have to deal with. I mean, right now, probably top of mind is nuclear war, okay, which we sort of forgot was a possibility, but, it's real. And another one is climate change is potentially an existential threat. And, if we're going to tackle that, we have to think about things like carbon capture from the atmosphere, better ways to do nitrogen fixation. And if you really think about what that entails, it means we are going to have to do the last 100 years of chemistry and materials upon which, our society is based. We have to do in the next 20 years. Okay. And that's unlikely to be something we're going to do by trial and error. The Haber process for nitrogen fixation, which is how all fertilizer is produced, is over 100 years old and hasn't been improved on and took a very long time to develop. For us to be able to develop things like that for, essentially to head off what's potentially an existential crisis, I think a quantum computer could be a major tool in our arsenal to do that. Classical simulations currently that we can do are not really predictive value for those kinds of problems. And for chemical reactions of large molecules involving transition metals. So, the way I look at it, and that, which is I think is reflected in Microsoft's perspective, is there are some really big problems that we need to solve, that humanity needs to solve, and quantum computer is potentially a way to solve them, to be interested in these things.
Yeah, I just want to build on. So I agree with what Chetan said. I think maybe the constants might not work out in quantum computing's favor with things like climate change. Hopefully we get those good qubits sooner rather than later. But building on what Sergio said, I think he mentioned complexity theory as a strong theoretical foundation, and I would add to that error correction and fault tolerance, because there are a lot of computing paradigms that have been offered. I mean, analog computing, or people talked about like DNA computing or things like this. I don't know. The fact that errors can be discretized and corrected in quantum systems is absolutely fundamental and is completely different from any other approach that you might take to computing. It means that quantum computers are in principle scalable. As long as we can get our errors to be, error rates themselves to be low enough and close enough to independent, we have no evidence at all that there are fundamental obstacles to building large scale quantum computers. So it's not just that we have these, there's great complexity results for analog computers, but we don't think we'll ever be able to build one because there's no compelling reason to believe that we can, store real numbers and compute with them to arbitrary precision. So this fact really cements the quantum computer as a fundamentally new and stable paradigm in computation. And without that, we wouldn't be sitting here.
I agree with that, but I do want to say that it's very hard to answer this because we're treating, money going into quantum computing as being like a single source, and it's really many different sources. And I think that the motivation for them can be very different. Some of them I think that in some measure, all of them are a combination of hope and fear. The hope that quantum computing will deliver on the promise that has been, been presented since almost 40 years ago now. And there's many hand-wavy arguments about why quantum computer, there's a very solid foundation of complexity theory, but there's also hand-wavy arguments about why quantum computing will be better at solving particular types of problems. And I think that people want to believe that, but that's not enough. I think that it has to come also with some level of fear, because if it's just hope, then it's fine for it to keep moving in the background. But there has been a growing feeling that while quantum computing has always felt like it's 10, 20 years in the future, recently it's felt much more real because of the fast progress in hardware demonstrations. And that has led people to look at what happens if quantum computing is real and we're not the first ones to get it right. And this goes from governments to commercial players that get to be on the leading edge, either by having very small advantages that compound greatly, or those that have such a long time horizon for the kinds of things that they do, that investing in something now that may not pay off in 5 or 10 years is still worth doing, because the things that they're doing now may still be affected by that.
Okay, so somebody in this room is going to write the book, Quantum Computing, Hope and Fear. Okay, just so you know. So related to that, so we all want to move the quantum computer into being. We're all part of this endeavor. And you can sort of adopt different strategies toward getting there. You can sort of go for the really long shot, try something declare that you're going after some goal that is, pretty out there, pretty ambitious. Of course, if you succeed, then everybody's very far ahead. Or you can take a more, I guess, gradualist approach. You can chip away at your error budgets. You can, try to refine and really grow slowly from the bottom up. I see representations of both those approaches. I see both of them both within industry efforts and also within academic labs. Like both of those styles of making progress are at play. So what do you think? What does it take? What's the right approach to move this forward? Some of you have declared yourself to be of one type or the other in those
Yeah, I mean,
strategies.
there's maybe a couple answers to that. I think my personal opinion is somewhat balanced on it. I mean, we need some of both. I don't think it's one approach or the other, but I guess speaking from experience, from the experience of somebody who's at, venture capital funded startup, which might be different than the experiences of other people in this room. Some of the gradual approach is almost necessary because that's how you get funding. You need to get milestones. You need to show by, the next time you need to raise venture capital from investors that you've made progress. And I think a few players in the field have tried to make more of the pitch that they're just going to shoot for the moon right away. But I think it's much easier to have the conversation with investors that you're, you can measure progress even quarterly or certainly every year. And so I think from the standpoint of venture capital funded startup, I think it's just a necessity to do that. And then the challenge we have is to balance that also with the understanding that, there's a long-term vision, which is fault-tolerant, error-corrected quantum computers. The solution to that's not going to be there by the next board meeting. And so we need to make sure we're also developing kind of our long-term technology roadmap. And maybe veering into another topic, I think that's actually where collaborations with academia for smaller companies like ours can actually be very helpful to kind of, work on the longer time horizon projects, sort of in the academic collaboration context, while still pushing forwards our roadmap internally in the company.
So if anyone has read Peter Thiel's book, 0 to 1, describing startups, that's a really good book that at one point in a later chapter, and he describes the kind of the attitude of an indefinite optimist or a definite optimist. So the indefinite optimist says, look, we have all these different approaches, we're funding them all, we'll see which one works. And that's actually that's how R&D basically works. And that's a good model, right? And that's basically what you do at the university. However, he although he doesn't say that directly, Peter Thiel also says that a definite positive, where you have a definite goal, a definite way of doing things, your milestones for the next quarter or year, is definitely how startups work. Definitely that's more industrial. But I would say still there's a big tendency to be indefinite because that way you never have to worry about your company failing or your project failing. That's the last thing we all want. So we try to be kind of indefinite as we can,
Sure.
as we can get away with. Okay. So for example, with the quantum supremacy experiment, I was really excited that that was a definite experiment and that we could fail. And then if we failed, no one wanted to fail. That's why it's kind of crazy to do it. But I figured if we fail, we're going to learn something and then we're going to know what to fix. So I say, it's risky to do definite experiments, but then it forces you to get things right, which in turn the group did. So it's read Peter Thiel's book. He really describes this quite well.
All right, so maybe on the topic of industry as it interacts with academia. So here's a challenge, or here's a question. Like, what's a result that's come out of academia recently that you think is a game changer for the quantum industry? Uh-oh.
I have a
This is one of
personal,
these definite optimism
I
situations.
have a personal
Ah,
bias.
good, okay, thanks.
And I talked about it, particularly for the neutral atom platform. And this is actually kind of tied to your previous question, where I think that it's important that you have a clear long-term vision, even if you don't have the most precise roadmap about how to get there. But it's a little bit like navigating in a foggy street. You know where you're going, and you can see a little bit ahead of you, and you stay focused on making that progress. But I think that sometimes you just have to you need to be flexible enough to take opportunities when they come. And I think that this is, I mean, it's a very hard judgment call when that happens. But like specifically something that came out of the academic labs that has been shaping our thinking about near and midterm algorithms is this ability to reconnect chips as part of the computation. And it's because it's not just the fact that it gives more flexibility, but the fact that it allows you to start thinking about a more sophisticated architecture where you can have functional areas in the same way that you do with things like ALUs within a classical computer. So moving away from this static chip where you have very, very costly ways of moving quantum information to just move the thing that's easy to move and preserve the quantum information. That has been quite instrumental in how we're thinking about the future for us.
I think the invention of good quantum LDPC codes has the potential to radically change how we build quantum computers in, I don't know, 5 years, maybe 10 years. These are codes that still have low weight parity checks, just like the surface code. They have some degree of geometric non-locality, but unlike the surface code, which encodes 1 qubit into n qubits, these encode order n qubits into n qubits. The existence, I mean, we use these codes every day in our, the classical analogs of these codes every day in our cell phones, and they're extremely powerful. We have known about these codes for about 1 year only in the quantum setting, and we don't know a lot about them yet. We don't know great fault tolerance protocols for them like we do with surface codes. We don't know very many architectures that are compatible with this idea of geometric non-locality, although the QuEra, yeah, I know. You mentioned them briefly in your talk. I mean, you can also envision doing this with like lots of crossovers on a superconducting device or something as well. It's not like there's no way to envision doing these things, but it will take innovation. But the payoff is there. Like your overheads will be so much smaller if you can harness this. And no one's even considered thinking about these questions because there was no real reason to do it. Building surface codes is already hard enough. Why should I pile on? Well, now there's a real incentive to do it, because if you can do it, your overhead is going to drop. You know, instead of 1 qubit in 100 qubits, you're going to get 20 or something, right? So I think this is a result in the last approximately 1 year that does have potential to revolutionize.
Just to change gear, this is about experimental work. As I've said, I'm really worried about how to make the qubits better. And I really enjoyed an experimental paper from Berkeley by Irfan Siddiqui's group having to deal with treating the surface of niobium and making better qubits. And what was great, it was very academic, like, and they studied it extremely well by going through the various mechanisms, TEM, XRF, other things, to do a good scientific paper. And you know, it's not this brand new algorithm or something, but I think it very much contributed to our knowledge on how to make qubits better. The interesting thing is I'm not sure all the conclusions are right because it's materials and you never know, it has to be reproduced. But the paper was done so well that it really adds a lot to the field.
Mm.
And that's the kind of thing that academia can do. That's not necessarily the kind of thing that an industrial group would publish. And it's very important.
Just a couple more examples. One, we work with superconducting qubits. We had a collaboration with a group in Germany that, John will know very well, to look at the TLS of the transmons. And I think those results are very interesting. They did some very careful experiments trying to point out in what particular part of the qubit you might have, a significant percentage of TLS. TLS is one of the dominant sources of noise, and ideas about how to fix it. So that it's still early days, but it looks fairly promising. If you could fix half of the TLSs, then you might lower your errors by a factor of 2. That's very significant. And more on the theory side, computer science side, which is more what I do. I like the work that Umes and others have been doing on certifiable quantum nest or things of that nature. I think benchmarks are super important, not just for noise, but also algorithmically and computationally, and to sort of make sure that the field is advancing. Of course, there are many metrics that are important to look at. Like you want to look at errors per gate, you want to look at T1 in the right context, but also algorithmically is very important to have good algorithmic benchmarks. And this is, I think that's a very promising direction as potentially one of the first computer science applications of quantum computers. It sounds, it doesn't need necessarily like the same size as a fault-tolerant quantum computer to do simulations in chemistry, things like that. But it comes with strong theoretical guarantees, cryptographic guarantees that this is a very hard thing to reproduce classically. And I think if we manage to do that in some intermediate level scale, I'm very optimistic we will find applications for that, because we always find applications for new computational capabilities. And it will be, very good for the field in general. So that's some work that the bases are being set now in academia, but I think they are likely to have important practical applications in 5 years or something like that, if we manage to scale the quantum computers at the same time that we're reducing the computational resources.
Jim, anything else since you're a recent convert, anything else from academia that they all should know about?
So, the nice thing about academia is I think academia is a little bit less invested in making sure that the big quantum experiment works out, right? So one is not afraid in academia to prove impossibility results. And that's something that's ready to search and going out to go find lower bounds or hardness and sort of draw the boundary on the other side, right? And the nice thing about when you draw the lower bounds or the complexity is it sort of should set the guide rails for how one goes about trying to solve these problems, right? It's not saying, hey, don't do it, or this is totally impossible. It sets the guide rails. I think the best example of this is NP completeness. And there's a lot of problems which we know are NP completeness, but there are these amazing SAT solvers that solve SAT formulas crazy fast, despite the fact that it's NP complete, right? And they work because they sort of look at very specific structures. It's not exactly the complete problems, and they work on a lot of these on many instances, right? So again, NP completeness, QMA completeness, dequantization algorithms, these are should be the guide rails with which one thinks about it. And then there's a lot to be learned there, right? Some people think of complexity results as upper bounds on algorithms. You can also think of algorithms as upper bounds on the lower bounds, right? So they're really two sides of the same coin.
Hey, I know you probably want to get on to the next question, but I actually want to double down on something that John said, about the importance of materials here, especially at least with solid state qubits. I mean, I realize the Rydberg atom case is quite different, or ions. And, I think in my mind, what industry is probably better at than academia is if, you have a set destination with a somewhat deterministic path, getting to focus on going on that set path is something the industry is relatively good at. Academia is a bit more anarchic. and freewheeling, and is very good at exploring a lot of phase space, sort of crowdsourcing problems and letting people explore lots of different directions. So through many people random walking, you can explore a lot of phase space, but it was not the most efficient way to get to a set destination along a fairly, narrow trajectory. I think, both of those are things you need. And when you are stuck or backed into a corner and hard to, having difficulty making progress, that kind of exploration is extremely useful because it gives you some kind of step function improvements that you wouldn't get by incremental progress. An example where I think that that's been extremely fruitful, and we've seen a couple of step function improvements, is actually in graphene. So in my mind, there were two, since the early days when people started doing experiments on graphene, there were two major step function improvements. One was going to these boron nitride substrates and using boron nitride as the substrate and as your gate insulator, having a high quality crystalline insulator. And that made a huge step function improvement in the quality of the phenomena you saw in graphene. And the second was going to graphite rather than metallic, rather than aluminum gates. These are kind of, probably for many people in the audience, these are in the weeds materials things, but they were absolutely essential advances, which came about really through a random walk of lots of people trying lots of different ideas, that most of which didn't work, and hitting on a few things, and then the whole field realizing their value and everybody adopting it. Okay, I can speak for our program, and maybe John, was saying some things that were quite similar. That very basic things like having better dielectrics, better gate alignment, some very specific materials things are where some of our problems are, and maybe even some of the most important problems, for solid state qubits. And, academia does have a track record of coming up with, ideas there. So, I would, list that.
Okay, so maybe I'll ask this last question. So one of the other things we do in academia is we shovel people over your way. I was recently, asked by some dean, whatever, to fill out some form, of course. And I think I was supposed to write out what subjects, what domain areas, what skills, and what ways of thinking should we prepare students. Let's see, I think the phrasing was so they can go out and have lives of significance. I thought that was rather haughty, but anyhow, so I don't know, it's lives of significance. So yeah, I think for subjects, I think I said statistics, science, and history were the three things you needed to teach students, but you guys didn't argue about that. Anyhow, so all right, thinking about either domain knowledge or skills or way of thinking, how should we prepare people to thrive in the quantum industry?
I don't know if this is what you're going for exactly, but I think that in addition to technical skills, there's a type of technical management, project management, how to organize yourself, how to work in a team that's not just you, or just not just you and your senior postdoc or something that, and I think I experienced this as much as anyone. I didn't really learn that in graduate school. And I think the sort of time limited nature of your PhD and the fact that you're supposed to you're supposed to control your own PhD and become the domain expert, usually it doesn't lend itself to learning how to work in a team. So if you have 12 people with PhDs who are, combining to work on, let's say, one apparatus, that's an unfamiliar situation, I think, to an AMO physics lab or, something else you might get in academia. So in theory, if you have that many people who are really skilled, you should be able to utilize them efficiently and synergistically, but it's hard to do. And if I could just submit my wish list universities, is that we could somehow include this sort of training as part of the curriculum. It's probably easier said than done, but that is kind of the wish list.
Well, I obviously don't know the answer to that question, but I think in general, university prepares people well to go to find jobs and industry. Of course, also for other things. Certainly in quantum, one thing that is happening is that the set of skills that are now required is becoming a lot broader. For instance, Jonathan mentioned software before, right? Software is a big problem. If, as you're trying to scale, it's not just a one-off kind of experiment anymore. It becomes a way more complicated system. If we are building a quantum computer, we kind of have to reinvent the whole software stack, like from the control to the operating system to the programming languages. So that's just like one example, but everything that gets to be done in the lab. One difference for sure between academia and industry is that, yeah, indeed, academia is more freewheeling, more random walks. You can go and do your own thing, and that's great because sure, through serendipity or for your particular ideas, you might come up with these interesting, big delta functions. Industry, indeed, as has been said, tends to be more of our, well, here's the path, and we kind of try to march together. So it's kind of a different way of working. It's more social for sure. And I personally enjoy it. Like, you're not sort of working on your problem for 4 days before you randomly find somebody, willing to listen to you. Like, normally you're actually working with a bunch of people on the same problem, and everybody agrees it's important, and everybody's, happy to talk to each other. One thing that I think you have to overcome if you come from a strong academic career is there is a little bit this tendency in academia of, protecting your authorship or protecting, I don't know, your name, like you want to put the paper out. You don't want to tell people results necessarily before you actually thought them through because they might scoop you or something like that. And in industry, it's completely the opposite. In industry, you want to make sure that everybody communicates freely, everybody can help everybody in their problems. If somebody else solves the problem for you, great for both, so it has to be, you cannot put, silos if you have like 100 people working on the same project. It's a sure way to fail, right? So it requires a little bit of adjusting, and there is still in quantum, because it's still very academic, a fair amount of emphasis still on, papers and things like that. And I think we need to move. We're moving away from that in industry, and we need to move more away from that. Like it's been mentioned many times, like the most important work is not necessarily the thing that is going to land you the next paper. I think you really, we need to lower the qubit errors, right? It doesn't matter if it's going to be a Nature paper, but if we don't do that, we're going to have a much bigger problem. So it's important to make sure that we create the space so that people can focus on the important problems and recognize that, even if they are not, if they're not going to end up in the cover of Nature.
Yeah, so you asked, what can academics do to help students prepare for industry jobs? I think software engineering skills of some kind is really essential. Just learn Python, like have some projects where you're forced to do a bunch of coding in Python, but it's a little more than that. Get comfortable with GitHub and things like this, or Git, just version control more generally. Get used to writing unit tests. I mean, people do numerics in an academic setting, and it's like, well, I did the numerics, here's my notebook or whatever. And like the only person that ever reads your code is you. That's just not going to fly in industry. So try to develop good software development habits. That's one thing. Another thing, industry hires interns. So, there are internships available at all the major companies, at least. I'm not sure what the status is at startups, but, send emails to people that you want to work with at companies. That's a major thing. Encourage your students to do that, to look for internships or to cold email people. The more junior the person, the more likely the response. Don't cold email John Martinis. He probably gets enough, or Chetan. So I think those are two really big things. Another one is you spend a long time during your PhD, at least most people do. I think there's probably exceptional people for which this doesn't apply, but they don't need my advice. You spend a long time learning how to fail repeatedly for months, right? Like this is an unnatural thing for many people, especially people who are clever enough and bold enough that they want to do a PhD in physics. They're not used to failing for months at a time. And this is something that you have to learn how to tolerate and even enjoy. And in industry, you can't just simply fail repeatedly for months. you have to keep pushing, and you have to know when something is good enough, and then you have to ship it in some sense. Like, this is a solution now. What is the next bottleneck? Now let's attack that. And that's definitely a different mindset. Not like, oh, I bet you I could get another factor of 2 if I just optimize this. No. What's the next bottleneck? Move to it now. The pace is faster. That's been a learning experience for me personally, and something that I wasn't accustomed to. And only upon reflection did I realize it was because I had spent so long relaxing in my ability to just play around with these factors of 2 and knowing that I can fail, and it would be fine. That's not really an option in industry. So you should learn how to fail for months at a time during your PhD. That's an important part of doing the PhD, but then you need to get over that as a modality in which you contribute. And then you need to keep your eye on the prize and have a steady march towards progress. That's, I think, key.
You have to learn how to fail fast.
Yeah, that's right. Make mistakes as fast as possible. John Wheeler.
And move on from that.
Yeah.
I have 3 things that I think have not been covered exactly as I want to tell them. The first one is events like this, I think, are super important. I think that having access to having visibility while being at school to what people in industry are doing about what people in industry are doing, how they think, what they care about. And this also comes together with, I think that in academia, of course, there's an impetus to train academics. And I think that when that is not thoughtfully controlled, it can lead to a perceived stigma for leaving academia. And I think that's something that needs to be very purposefully controlled, that to encourage people to go into industry and to see the value of the work that is done in industry. The second one is, second and third are related to communication. I think that in academia, we learn a very specialized and sophisticated way of writing that after many years in academia, you come to appreciate the beauty of, but it's very hard to read an academic paper if you're not an academic. And that being in the mode of only writing with such language makes it very hard to communicate with others that don't have that background. So learning how to write and how to constantly write so that there is a track record of what you're doing in a way that allows others to build on top of it. And it's related to good software practices, but I think this is much more general than that. And the last one is similarly related to that. Being comfortable, there's a lot of things in academia that are very uncomfortable, but something that I don't think there's enough exposure to is being uncomfortable by being put in a group of people that is very different. And we create a lot of verbal shorthand notation to communicate efficiently, but it makes it very difficult to talk with people that don't have that shorthand notation. So I think that something that I would like to see is more events, more collaborations where people are put outside of their comfort zone to have to not just explain what they do, but have to in real time come up with a common develop a common language with someone else from a different background to really be able to convey not just what they want to say, but to make sure that the other person is understanding, because that is crucial to working in large teams that have very different backgrounds.
Yeah, so I wanted to just follow up on 2 of the points. So just doubling down on what Steve said, and maybe taking to the extreme is, I think in academia, we typically focus on solving problems, on finding solutions. There's another class of activity which is to make decisions. And, when you were trying to, and that's kind of, this idea of like failing repeatedly, which is you find a solution, you keep working till you found the solution. If you don't have enough information, or you don't have the right solution, you just keep working. But when you're trying to make a decision, by the time you have all the information, it's probably too late. We in academia, tend to focus on solving problems, and that's what we do. You solve a problem, you write a paper, but we actually make lots of decisions. You decide to go to grad school or not go to grad school. You decide to go to grad school in physics or computer science, to do, string theory or quantum information. You make lots of decisions, but we don't actually think very much about the decisions that you make, or even train people to make decisions. And in industry, you actually have to make decisions all the time, precisely because in many cases, you're trying to go along some set path, and you're not doing random walk, which enables you to not make a decision, because different people can explore different things and everyone can decide their own thing. If you're trying as a team to do something, you have to make some decisions. So you have to get comfortable with making decisions with incomplete or imperfect information, and to learn how to make those kinds of decisions. And that's a very big difference that we don't particularly teach or train people how to do. A second thing is, if you have a team, in a company working on trying to, especially in the hardware side, a team of 50 or 100 people, you don't need that 50 or 100 people to all have PhDs. In fact, it's better if they don't, to be honest with you, right? You don't need 100 people with PhDs in physics, or PhDs in physics and computer science and math. You probably need, I'm almost certain you need some mix of people, many of whom don't have PhDs, who have extensive, perhaps industry experience or master's degree, or some people who have a bachelor's degree and no graduate degrees. Because in a team of that size, there will be a fair amount of specialization, and there will be maybe someone whose job is, just to operate the E-beam lithography system, and they get very good at it, and they operate one tool, or to just do a certain type of measurement, or to focus on packaging. There are lots of, the larger a team gets, if you want to, efficiently use more budget, it's going to involve specialization. And what's often difficult is, while there are lots of people with very specialized skills that you can hire from industry or out of fresh out of universities, they often don't. There is an impedance mismatch between those people and the people who have PhDs and are deep experts in quantum computing. So I think maybe the thing that we probably haven't done a good enough job is, we have a lot of people with deep expertise who've gotten PhDs, but not enough of people who are not deep experts in quantum computing, learn enough about other things, who could be part of that team, have not learned enough of the language of quantum computing to effectively work together with people as a team. So it's sort of that little bit of extra knowledge that would enable people to work, productively as a team, is something that I find is hard to find.
Great. Well, in terms of learning how to make decisions, I'm going to decide that this is the end of the panel. So first of all, let me just say what a fabulous panel this is. It's really impressive. Thank you. And then, do you want to say something to wrap us up?
Yeah, sure. Yeah, actually, so just following up on that, it's been a fantastic day between, yeah, so it's, from my perspective, it couldn't have gone better in terms of, we had a sequence of wonderful talks and a really great panel, moderated really well. And so I feel there's a lot to chew on at this point. The staff have been nice enough to, I hope when we go out, there should be a tea out there so we can chew on even more and continue this conversation. So thanks everybody for attending and continue the conversation.